Okay, so today we're countering some mathematical induction questions. This kind of questions are really common. First of all, you have to prove some series, and then after that, you have to use the theorem that you just proved to find something else. So they're both honestly really straightforward. So let's just do it. Part A is honestly if you the thing is that you have to memorize how to write the format for mi, and if you can do that, you could finish any type of mi questions. But so let's say when n equals 1, left hand side is oops r from 1 to 2 of r squared, which is 1 squared plus 2 squared, which is 5. RHS is 1 over 3, 1, 2 times 1 plus 1, 4 times 1 plus 1, which is just 5. Because that's 3 and that cancels out. This implies P1 holds. Okay. Now we assume pk holds for some positive integer k, i.e. We have from r from 1 to 2k of r squared is equal to 1 over 3k, 2k plus 1, 4k plus 1. Okay? And then we have n equals k plus 1, which means left hand side is from r equals 1 to 2k plus 2 of r squared, which is frankly speaking just 1 over 3k, 2k plus 1, 4k plus 1, plus, excuse me there, 2k plus 1 squared plus 2k plus 2 squared. And we have, which means I think we have 1 over 3 of, excuse me there, I'm just trying to expand of the brackets here. We have 8k squared plus 6k plus 1 plus 4k squared plus 4k plus 1 plus 4k squared plus 8k plus 4, which means we have 8k cubed over 3 plus 2k squared, 4k squared, 4k squared, which is just 10k squared, plus that is k over 3 plus 4k plus 8k, so that's 12 plus 1 over 3. Is that 12 plus 1 over 3? 1 over 3 plus 4 plus 8 is just 37k over 3. And then plus we have 5. Yeah. So that's LHS. And it's impossible to go backwards to the other side. So let's start from right hand side this time. Oops, shouldn't have written that there. Let's start from right hand side this time around. We have 1 over 3 k plus 1, 2k plus 1 plus 1, and then 4k plus 1 plus 1, which means we have 1 over 3 of k plus 1, 2k plus 3, and then 4k plus 5, which means we have k plus 1 over 3 of 8k squared plus 22k plus 15, which means we have 8k cubed over 3 plus 22k squared over 3 plus 15k over 3 is just 5k plus 8k squared over 3 plus 22k over 3 plus 5, which means we get the exact same thing 5 plus 22 over 3 should be 37 over 3 plus 5. And they equal the same thing. Oh, let's write equal LHS here, which means pk plus 1 holds when pk holds. Yes, it does sound like a swear word in Cantonese, but I absolutely do not care. Which means Pn holds for all n belongs to the integers. And that's it for part A. It's really straightforward. If you can't do from LHS to RHS directly, you could do LHS equals Fn, Fk, RHS equals Fk, and then if they equal to the same thing, that means you got Mi done, and you've proven the theorem is true. So part B, we have to prove whatever that's called. So let's start from the right hand side here. We don't need Mi for this one. Right hand side is just k from I equals 1 to n of r squared. Yes, I didn't remember it's wrong. That was great. Which means we have, we could just use the theorem. We could just use k over 3. Because it's n, not 2n. So we have n equals n over 2 instead. Which means we have n over 2, n plus 1, and 2n plus 1. And then we'll have k over 6 of kn over 6 of 2n squared plus, we do not need that, kn over 6 of n plus 1 2n plus 1, and that equals to LHS, which is just the thing we proved in part A, 1 over 3 n 2n plus 1 and 4n plus 1. This implies we could cancel out the 2n plus 1s, and we could cancel out the 1 over 6s, which implies, and we can cancel out the n's, which implies we have k times, implies we have k n plus 1 is equal to 2 times 4n plus 1, which implies kn plus k is equal to 8n plus 2. We need subject as n, so we have n equals 2 minus k over k minus 8, and that's the exact result we want, and this is the end of this really common MI question.